So far we have force of gravity is 4 newtons and tension force is unknown. We're calling downwards the y direction just because we know the object is going to be moving downwards and that's the only motion. So we may as well call that positive. In that case, what would the sum of the forces look like if we just add together the forces we've got? What would that have to include?
So Fg minus Ft?
Yeah. I mean, strictly speaking, it's the force of gravity as a vector plus the force of tension as a vector. But if you look at just the y components, the force of gravity is positive 4 newtons. If we think of these as just y components, we've got force of gravity in the y direction plus force of tension in the y direction equals mass times acceleration in the y direction. We know force of gravity is positive 4 newtons. We don't know the force of tension, but we know it's acting upwards, which we're calling the negative y direction. So we'll treat that as plus negative force of tension equals the mass, which we know, times the unknown acceleration in the y direction. And assuming the gravity force is stronger, assuming this is accelerating downwards as it tumbles, we can assume acceleration is positive since it's in the downwards direction. Then how many unknowns do we now have?
Would it just be 1 because we have acceleration of gravity?
Well, this isn't the acceleration of gravity, though. This is the actual acceleration of the disk as it tumbles down the rope. So that is presumably going to be slightly less than the usual acceleration of gravity, less than 10 meters per second squared. Because if it were just in free fall, acceleration would be the acceleration of gravity. But the fact that this rope is here slows it down somewhat. It's not enough to prevent it from falling. This is going to be falling as it tumbles or rolls down the rope. But it is going to be traveling more slowly than under gravity alone. So it looks like we do have 2 unknowns here. We don't know the acceleration and we don't know the force of tension. So we're going to need more information. Is there anything else we could add up and set equal to something here? What else has to add up to a certain known amount?
Can we say anything about torque? But isn't there a net torque since it's unwinding?
Yeah, this is presumably, I mean, this isn't staying still. It's not even spinning at a constant rate. It's spinning and getting faster and faster as it tumbles down the rope. So there is a net torque, but that's going to be a fairly predictable net torque. In fact, in general, what should we expect the torques to add up to? In general, what does torque do to an object? We know force causes acceleration. What does torque do to an object?
Makes it rotate.
Yeah, or I would say rather it changes its rotation. You don't need a torque for an object to be rotating. If it's already rotating, it'll just keep rotating without needing any torque at all. So an object that's just rotating but not changing its rotation doesn't need any torque. Torque causes a change to the rotational motion. In particular, if we construct a similar equation to this, we know the force equals the mass times the acceleration. What's the rotational version of mass?
Moment of inertia.
Yeah, so we can say moment of inertia times, and then what's the rotational version of acceleration?
Angular velocity?
Angular acceleration, I would say. Angular velocity is the rotational version of translational velocity. But the rotational acceleration, alpha, is the rotational version of translational acceleration. So translational acceleration is how fast the translational velocity is changing. Angular acceleration is how fast the angular velocity is changing. For instance, angular acceleration might mean that the object is spinning faster and faster and faster, or slower and slower and slower, or it might even be keeping the same rotational speed, but changing the axis it's rotating around. Or,
I don't think we've...
Sorry, what was that?
We've never seen alpha, so is there a different way we would be expected to do this?
I don't think so. I mean, that's the rotational version of acceleration.
They posted a solutions for it, and they used like linear momentum. I just didn't know how to follow the solutions. They used linear momentum and angular and then like divided the equation somehow.
Yeah,
I
that
can also
doesn't.
send that.
I don't think that's really a reasonable way to approach this, though, because it is accelerating, isn't it?
One second. I just might have misunderstood it, but I can send it because I'm confused.
Because the whole idea is that a torque can cause the angular velocity to change. The way these quantities are related are you got angular velocity. And what does angular velocity actually mean? Like if an object has angular velocity, what are we saying?
It's rotating.
Which means what's changing? What does it mean for an object to be rotating?
Like its direction, not direction, but the direction of its velocity.
I mean, for instance, if I've got an object that's spinning, what is it about that object that's changing as time passes? Assuming it's spinning at a constant rate. Like if an object has translational velocity, you can just say its position is changing as time passes. But if it's spinning, what property of it is changing as time passes? Or how would you describe how fast it's spinning numerically?
Number of revolutions?
Revolutions, that is one way to do it. You could say number of revolutions per second. But that kind of gets cumbersome if you're talking about not a whole number of revolutions. Like if you're dealing with 5 2/3 revolutions per second or something. What's a sometimes more precise way of describing how or some fraction of a revolution? Like if you're only revolving like this much, instead of describing that as a fraction of a revolution, how would you describe numerically this much rotation?
In radians per second?
Yeah.
Like or angle per second?
Yeah, exactly. It is an angle. We'd be measuring it in radians per second or degrees per second or revolutions per second, but radians is really the most natural measurement of an angle. And angular velocity is talking about how much the angle is changing as time passes. So we can write that as d theta dt. Angular velocity is the derivative of angle in the same way that translational velocity is the derivative of position. Translational velocity means your position is changing as time passes. Angular velocity means your angle is changing as time passes. That is, you're changing which direction you're pointing or which direction you're facing. So that's angular velocity, how fast the angle is changing as time passes. And we describe that in radians per second. But the angular acceleration usually written as the Greek letter alpha, lowercase alpha, is kind of related to, I mean, for translational acceleration, how do we define translational acceleration?
F net over mass.
That's what causes the translational acceleration, but what is translational acceleration?
Meters per second squared, like how fast you're speeding up.
Or how fast your velocity is changing. More specifically, in terms of calculus, it's the derivative of velocity with respect to time. So for the translational quantities, translational velocity v is the derivative of position, dr dt. So if r is like where you are relative to some origin point, which does count as a vector because we're talking about how far in a given direction you are from the origin. Velocity is the derivative of position as a vector. And then acceleration, how do we define that as a derivative?
dv over dt?
Right, dv over dt. And since velocity itself is a derivative, we could also think of acceleration as the derivative of position. That is the second derivative of position. So velocity is the first derivative of position, acceleration is the first derivative of velocity, and therefore also counts as the second derivative of position. For rotational motion, we use a similar progression of terminology. Angular velocity is the first derivative of angle, like which direction you're facing. Angular acceleration is the derivative of that. Angular acceleration is the derivative of angular velocity with respect to time. In other words, how fast your angular velocity is changing. And since angular velocity itself is a derivative, angular acceleration can be thought of as the second derivative of angle. So that means that angular velocity just means you're changing your orientation. Like as time passes, you're changing which direction you're facing. So this object has angular velocity. If I change that either by slowing it down or by making it spin faster and faster and faster, that counts as angular acceleration. But also if I just tilt which way it's spinning, if I tilt what axis it's rotating around, that also counts as angular acceleration. Because angular velocity is a vector. It has direction given by the right-hand rule. Like for instance, if this is spinning like this, if I curl my fingers in the direction it's rotating, the angular velocity right now is upwards. If I tilt it, the angular velocity is now towards me. So the angular velocity changes direction if you tilt what axis the object is rotating around. That counts as angular acceleration, even though it's not changing how fast it's spinning, just what axis it's spinning around. In the same way that an object moving and changing direction of travel counts as translational acceleration, even if it doesn't change how fast it's moving. Any questions on that so far? And we can set up some similar equations involving torque versus force also. The usual equation involving force and translational motion is that the sum of the forces equals mass times acceleration. That is, you apply a net force to an object, it's going to accelerate translationally. And the mass represents how difficult it is to make it accelerate. For torque, we have a very similar sort of setup. The rotational version of force is torque. The rotational version of acceleration is rotational acceleration. And the rotational version of mass is moment of inertia. So the sum of the torques should be moment of inertia times angular acceleration. And by the way, this is only true if the moment of inertia doesn't change. This is one of the unusual things about rotation as compared to translational motion. For translational motion, mass doesn't really change. As the object doesn't break apart or anything, its mass stays the same. But for rotational motion, how can the moment of inertia of an object change?
Like if it's a point mass and it gets closer or farther from the pivot?
Yeah, if you've got just like an object on a stick and you're spinning around, but the object moves closer in towards the hinge, it's now got a different pivot or different moment of inertia. Or for a more complicated extended object, if some of the mass changes how far it is from the center. Like if you're spinning around with your arms outstretched and you pull your arms closer in, you're taking some of your body's mass and pulling it closer to the center of rotation. So you'd be decreasing your moment of inertia. In cases like that, this equation does not hold. The idea that the total torque equals moment of inertia times angular acceleration, this is only true if moment of inertia doesn't change. But as long as moment of inertia is constant, this should be fine to use. Any questions on that so far?
I'm just confused. I mean, I don't know if this is one of her old practice files, but she gave it to us. But since we've never seen that topic, is there another way to define angular acceleration?
Not really. It is just the derivative of angular velocity. It's how fast the angular velocity is changing. And you make changes to that either by changing or you make that happen by applying a torque.
Okay, thanks.
And if we take a look at the torques here and assume that they add up to moment of inertia times angular acceleration, what would be a good point to treat as the pivot point here? If we say this is rotating, what's it rotating around?
The center of the disk.
And not exactly. I don't think the center of the disk would really work well as a pivot point here. Because if you imagine the motion of this object, as it rolls down the rope, what single point on this is most closely being held in place, or closest to being held in place? Oh, actually, no. Yeah, I was thinking at the connection with the rope, but actually we're talking about the moment of inertia around its center. So we probably should treat the center as the pivot point here, since that's the formula we have. We could treat the point where the rope is connected as the pivot point. I think that seemed more intuitive to me because that's the point that it's rotating around. But we don't have a formula for its moment of inertia around the center, and that would be more complicated to determine. So let's go ahead and treat the center of the disk as the pivot point. So treating that center as the pivot point, we have a formula for moment of inertia, so we can use that to calculate I. But also treating the center as the pivot point, what force or forces are providing torques here?
Would it just be tension?
Yeah, tension's the only one. So we're going to have torque from tension, and that's it. Torque from tension. So torque from tension has to equal moment of inertia of the disk times angular acceleration. And we know that the moment of inertia is mr squared over 2. Any questions on that so far?
Really quick, when in the top right with the red equation, when you say force of y equals mass times acceleration of y, you're just talking about the y components since there are no x components, right?
Right, looking at just the y components.
Okay, perfect, thank you.
And yeah, if we wrote out an equation for the x components, it would just be 0 equals mass times 0, because there's no forces in the x direction and no acceleration in the x direction. In fact, in this case, because there's only one dimension of motion or one dimension of forces, we can almost treat force as being like a scalar. It is technically still a vector, but we don't really have to worry about directionality other than up versus down, which we're treating as negative and positive. Going back to the torque for a moment, how would you write out torque of tension here? How do you usually calculate the strength of a torque?
Would it just be the radius times the force?
Yeah, because if we draw in the radius vector from the pivot point to the location of the force, what's the angle between that radius vector and the force vector?
90.
Right, that's a right angle. And so if we write out radius times force times sine of 90 is just 1. So the torque from tension is just going to be the force of tension, which we don't know, times the moment arm, which is the full radius of the circle. That has to equal mr squared over 2 times the rotational acceleration. And we can simplify this a little bit, because what shows up on both sides here?
The radius?
Yeah, so we can divide both sides by r and at least cancel out one of the radii here. So we get force of tension equals half the mass times the rotational acceleration. Oh, and we know the mass also. We may as well fill that in too. We know the mass is 0.4 kilograms. So force of tension has to be 0.4 times 2 would be divided by 2 would be 0.2 kilograms times the rotational acceleration. So we now know how the force of tension is related to the rotational acceleration. Whereas from the force equation, we got how the force of tension is related to the translational acceleration.
What happened to the r in that equation?
Oh, that's right. We do have r. I forgot about that. So that still has times r. And what is r here?
Oh, 0.05.
Yeah, so let's fill that in as well. 0.4 times 0.05, that's probably be easier as fractions. 4/10, so 2/5. 2/5 times 0.05 is 1/20. So that'll be 2 and 20 reduced to 1 and 10, so we get 1/50. Then we're dividing that by 2, so we get 1/100th. So overall, the force of tension should be 1/100th, or 0.01. And we still have units of kilogram meters times the angular acceleration.
Really quick, where did you get the torque equation? I was looking on the equation sheet and that's not one of them given to us. So how did you come up with that one?
It's the rotational version of the force equation. That the forces from Newton's second law, the sum of the forces is mass times the mass times the translational acceleration. The rotational version of Newton's second law, as long as moment of inertia does not change, is that the sum of the torques equals moment of inertia times rotational acceleration. Because moment of inertia is the rotational version of mass, and rotational acceleration is the rotational version of translational acceleration.
Got it, thank you. If the inertia were to change, we wouldn't be able to use this at all.
Right, this only applies if the moment of inertia is constant. Ultimately, the reason for this is that, I guess the more foundational equation would be that the sum of the torques causes a change to the angular momentum. If we look at this in terms of momentum, going back to the idea of impulse, the sum of the forces equals the change in momentum over change in time. I think this is probably a more fundamental definition here, that the sum of the forces is the change in momentum over the change in time. I guess impulse would be if we multiply both sides by time. But in general, the total force is the rate of change of momentum. Formally, that should be a derivative also. The sum of the forces tells you how fast the momentum is changing. The rotational version of that would be that the sum of the torques equals the rate of change of angular momentum. So the total force tells you how fast the translational momentum is changing. The total torque tells you how fast the angular momentum is changing. So we can define both of those in terms of derivatives. This is basically Newton's second law written as a derivative and Newton's rotational second law written as a derivative. But if we fill in some other definitions, what does translational momentum mean?
Mass times velocity.
Right. If we fill in mass times velocity here, also in general, mass should not be expected to change. We should expect the mass of the object to stay constant. And what could you do with a constant multiplier inside a derivative?
Take it out.
Yeah. So we end up with sum of the forces equals mass times dv over dt. And what's dv over dt? What do we call the derivative of velocity?
Acceleration.
Yeah, exactly. That's the translational acceleration. So the idea of sum of the forces equals mass times acceleration, that ultimately comes from the idea that the sum of the forces equals the rate of change of momentum. But if you substitute in the definition of momentum, translational momentum, and pull out the mass as a constant, you end up with mass times acceleration anyway. So these two statements are equivalent. You can say the sum of the forces equals the rate of change in momentum, translational momentum. Or you could say the sum of the forces equals mass times translational acceleration. Those two statements are saying the same thing as long as we assume the mass of the object does not change, which it typically shouldn't. If we try the same approach on torque, the total torque equals the rate of change of angular momentum. But how do we define angular momentum in the first place?
Moment of inertia times angular velocity.
Yeah, so we can write the sum of the torques as change in moment of inertia times angular velocity with respect to time. And here's where things get a little more complicated. Moment of inertia is not always constant in the same way that mass is always constant. So we can't necessarily pull out the moment of inertia as a constant. If the moment of inertia is changing, we just have to leave it as this. But if the moment of inertia is constant, then this equals, again, we could pull out the constant multiplier and get moment of inertia times rate of change of just angular velocity. And what do we call the rate of change of angular velocity?
Angular acceleration.
Right. So we can make that substitution and get moment of inertia times angular acceleration. So if the moment of inertia is not changing, then the total torque has to equal moment of inertia times angular acceleration. I think it would be safe to say that the idea that total torque equals rate of change of angular momentum is a more foundational or more basic assumption. This is Newton's second law written in terms of angular motion. If the moment of inertia happens to be constant, which it is here because the object is not changing its shape or size, then we can also write that the total torque equals moment of inertia times angular acceleration. Any other questions on that comparison so far? So let's go back to these equations we've got. We know that from the torques and the fact that the total torque equals moment of inertia times angular acceleration, we can say that the force of tension, even though we don't know what it is, has to equal 0.01 times the angular acceleration. But we can also use this fact here, that's what we had from the total force in the y direction. If we simplify this a bit, we've got 4 newtons minus force of tension equals 0.4 kilograms times the acceleration. And we don't really even need to say acceleration in the y direction because that is just the total acceleration. It's only in the y direction anyway. At this point, it looks like we have 2 equations. But how many unknowns are we dealing with?
3.
Yeah, we don't know the force of tension, we don't know the translational acceleration, and we don't know the rotational acceleration. So that still needs one more equation. We need one more fact linking these together so that we have a system of as many equations as we have unknowns. And that one more fact, what else do we know about translational motion and rotational motion? How do those have to be related in this case where it's unwinding without slipping?
I feel like it just has to do with the hint that they're rotating same speed, opposite direction.
Does that work? That doesn't actually seem valid. I mean, the point on the, if we look at a point on the edge where it's attached to the rope, that point is not actually moving at all. Because as it rolls down the rope, the point that's attached to the rope can't move. So I don't think that hint is really going to be helpful here. Because the point that's attached to the rope is not moving at all. The center of mass is moving down, and the other edge is also moving down. There's no single point on this entire disk that's moving up. So I don't think that hint is really useful here. But I think we can use a relationship between translational motion and rotational motion. Have you seen how angle is defined in the first place in terms of radians?
I don't think so.
Sorry, what was that?
I don't think so. Like, what do you mean?
Like when we say an angle's radian measure is 1.7. 1.7 what? What does 1.7 radians actually mean?
I have no idea.
That might be a better place to start then. If we go back to a circle, let's say you have a circle and we're drawing out some sort of angle on it. If we want to describe how big this angle is, let's say all you can measure is distance. What's a distance you can measure that's associated with this angle?
Do you mean like the diameter of the circle?
The diameter of the circle is more a property of the circle than the angle itself, though. Is there any property of the circle that's specifically related to this particular angle that wouldn't be the case for a different angle? Or that would change if we change what the angle is? Like if we change the angle, if we change the angle from larger to smaller or to larger still, is there anything we could, any distance we could measure that's changing if we change the angle around?
The circumference?
The circumference of the circle?
Yeah.
If I change the angle, the circle still has the same circumference. But what portion of the circumference is changing?
The part that the angle is like encapsulating.
Yeah,
The arc
we've got
length?
this section. Yeah,
Arc length, that's the word.
Yeah, that's a good way to describe it. The arc length that's enclosed inside this angle is changing. So if we focus on that arc length, the arc length does depend on the angle. That is, if we were to make the angle larger, we'd be increasing the arc length also. So we can use the arc length as a description of how big the angle is. The only problem is the arc length depends not only on the angle. Like if I just say I'm drawing an angle whose arc length that encloses an arc length of 3 centimeters. The problem is if you're using a larger circle or a smaller circle, then if you were to draw another arc length that is also 3 centimeters, then you'd have a smaller angle than I do. So if we want to specify an exact angle, you need not only information about the arc length, but also what other information?
How big the circle is?
Right. And we would usually describe that in terms of its radius. So let's say you know the angle or the arc length and the size of the circle. If I tell you this angle cuts off 3 centimeters worth of a circle whose radius is 2 centimeters, that should be enough information to specify the angle. But ideally, we'd like to be able to describe the angle with just a single number, not describing it as a pair of numbers, an arc length and a radius. So what we do is we talk about the ratio of arc length and radius. We describe the angle as the ratio of arc length over radius of the circle. If I say that the angle has a ratio of, let's say, 1 to 5, 1/5, I'm saying that this angle cuts off an arc length that's 1/5 of the circumference of the circle. You could duplicate that on your own circle no matter what size the circle is. If you just draw a circle and draw an angle that cuts off exactly 1/5 of the circumference, then you have the same angle I do, even if you're using a differently sized circle. This is what radian measure means. Radian measure is describing what's the arc length that the angle cuts off as a fraction of the radius. If we say that the radian measure of an angle is 1.7, what we're saying is that the arc length that the angle cuts off from the circle is 1.7 times the radius. And this is why we call it radian measure. Radian in the sense of defined in terms of the radius. Did we ever learn this in DL? Was it ever covered in a geometry class?
She mentioned arc length in lecture, but we didn't really go into it.
This is ultimately how angle is defined in the first place. This is not so much physics, this is geometry. That the way we define angle, the meaning of radian measure is that the radian measure of an angle is the ratio of the arc length that cuts off from a circle to the radius of the circle. So if we say the radian measure of an angle is 1/2, that means the arc length is half the radius. Or that is, it's an angle that's large enough that it cuts off an arc length that's half the radius. And because of this, radian measure is really the most natural way to measure an angle. It actually has a meaning in terms of the distance that the angle cuts off from an arbitrarily sized circle. Whereas degree measure is not really meaningful in a mathematical way. Like, what does 1 degree mean, for instance? If we describe an angle as 1 degree, what's the meaning of that?
It's a really small angle.
It is a really small angle, but specifically how
axes.
small? What's a number of degrees that actually has some specific meaning, some true physical meaning? Or I guess I should say some geometric meaning.
Like 90 degrees?
Right. 90 degrees is a right angle. So you could say 1 degree is defined as 1/90th of a right angle. But there's nothing special about 90. 90 is not really meaningful in a mathematical sense. If I draw a line and a line perpendicular to that line, perpendicularity has some meaning. It means that I've just split up this rotation into 4 equal pieces. But there's nothing about this that has the number 90 embedded within it. There's nothing special about 90 as a number associated with a right angle. It's just that 360 as a number of pieces to cut the full revolution into is convenient to work with because it has so many nice, neat whole number factors. You can easily divide 360 by 2, by 3, by 4, by 5, by 6, I think 8. Yeah, 8, 9, 10, 12. It has a lot of nice, neat whole number factors. But there's nothing mathematically meaningful about 360. So degree measure, really there's no reason to use degree measure other than because we're used to it. But radian measure actually has this meaning. The radian measure of an angle is arc length over radius. And this means that it's remarkably useful for making comparisons between an angular measure and a distance measure, the distance around the circle. Specifically, it means that we have angle, let me get a theta here. By definition, angle is equal to arc length, which we usually call S, times the radius. Make those capitals. So if the arc length is S and the radius is R.
Didn't you say it would be angle is arc length over radius?
Oh yeah, sorry about that. Arc length divided by radius. I would think I was accidentally jumping ahead to a different formula. So in this diagram, if we've got an angle of theta and a circle with radius r, the angle theta cuts off an arc length s, such that the angle is defined as arc length over radius. This also gives us the reason why, well, if you're talking about a full revolution, how much of the circle are you covering?
2 pi.
Right. Or rather 2 pi times the radius, but then you take that 2 pi times the radius and divide by the radius, and you're left with 2 pi. So this is the reason why 1 full revolution is 2 pi in radians, because the arc length that's captured by the angle would be the full circle, the full circumference, the full 2 pi r. Then we divide by r and we get 2 pi. So that's the reason why arc lengths or why angles in radian measure tend to be written as some fraction of pi, because the full circumference is 2 pi r, so the full revolution is 2 pi. We could also rearrange this a bit. If you solve this for arc length, what do you get?
Theta r.
Right. Which means that as long as you're using radian measure, there's a very convenient formula for arc length. Arc length is just the radian measure of the angle times the radius of the circle. If you use degrees, this needs an extra times pi r over 180 to get it to balance out right. But in radian measure, you have a much more natural formula. Arc length is just angle in radian measure times the radius of the circle. And this actually gives us a very useful way to relate translational motion and rotational motion. If you've got an object moving on a circular path or a circle-shaped object rolling, whether it's on the ground or rolling down this rope, the distance traveled by the object is the angle it has rotated so far times the radius. So if this has rotated, for instance, let's say 3 revolutions so far, you take the angle of 3 revolutions, 3 times 2 pi, multiplied by the radius of the circle, and that tells you how far it has traveled down the rope so far. We can also do a bit of calculus with this. We have distance. How do you turn distance into speed? How do we define speed in the first place?
Distance over time.
Right. Or more formally, a derivative. If we take the derivative of both sides with respect to distance, or sorry, with respect to time, we get d theta dt, and then radius is a constant. We're assuming the radius stays the same the whole time, so radius can be pulled out. Derivative of distance is translational velocity, but what's derivative of angle?
angular velocity?
Yeah, we get the angular velocity here, defined as d theta over dt. So when we take the derivative, we get translational velocity equals angular velocity times radius. We can use this as a relationship between translational velocity and angular velocity for any situation where the radius does not change. That is, if the object is rolling without slipping, whether on the ground or down a rope. We could also take the derivative again. What happens to velocity when you take the derivative?
Acceleration.
Right. So the translational acceleration equals, and then derivative of angular velocity is angular acceleration. So we get angular acceleration times radius. So this is a relationship we can now use here. That's our third equation. Because we were missing some information here. We knew how tension was related to translational acceleration, and we knew how tension was related to rotational acceleration, but we needed one more piece of information because we had three unknowns. This is our third equation. This is our third piece of information. So using these three equations, we should now be able to solve the system of equations. One way to do that, for instance, would be to replace translational acceleration with angular acceleration times the radius of the circle. Use that substitution in this equation here. That'll give you an equation with just tension and rotational acceleration as the only unknowns. And R here will still be the 0.05 meters. And then we also have a second equation relating tension force to angular acceleration. That's two equations, two unknowns, once you make that substitution. And then you could either use another substitution or elimination to solve for, or to get an equation with just one variable. For instance, in this case, you might want to isolate angular acceleration and plug that into the other equation. That'll ultimately get you an equation with just tension as the only unknown. And then you can solve that equation for tension. Any other questions on that one? All right, then keep the math going on that, solve the system of equations, and that should give you a value for all three of these, really. The tension force, the translational acceleration, and the rotational acceleration. So try that out.
Thank you.
You're welcome, and I will see you next time.
Thank you.